Hi, I'm Abe Ellison. I work with Professor Keith Julian. I'm a fourth year PhD student in applied math. And today I want to talk about gyroscopic numerical methods. So rapid rotation creates this gyroscopic alignment in fluids through the Taylor-Proudman theorem. This theorem basically equates Coriolis forcing with pressure gradient. And what you end up with is invariance along the vertical direction in your fluid flow. And so we want to build in to our fluids methods, our numerical methods for simulating fluids, a coordinate system and then a spectral basis for this gyroscopic alignment. And so this leads us to a class of geometries we call the stretched cylindrical geometries. And each geometry lends itself to a particular spectral basis. So what we do is define these coordinates, s, phi, and eta, and they're related to Cartesian x, y, z in this way. S and phi are your polar coordinates, and then eta is your cylindrical height. And we multiply eta by this height function h of s. And this is actually our stretching function. So here you can see if you choose a parabola for h of s, then you end up with parabolic upper surface. And likewise here, we multiply that parabola, which is this dent in the top, by the spherical function square root of 1 minus s squared. And that ends up giving us this dented sphere or a blood cell type geometry. And so we want to be able to simulate fluid flow in geometries like these. And so to do so, we define our spectral basis. And so it's indexed by m, l, and k. And it has, as part of it, the mth azimuthal Fourier mode, e to the im phi. This s to the m guarantees regularity. And then we multiply our functions by h of s to the l. And that will lead to a Cartesian polynomial in z, because PL of eta is a degree L polynomial in eta. So you can see z to the L is eta to the L, h of s to the L. And then Q are also polynomials, but these are in the s coordinate. And we choose P and Q properly so that we get orthogonal polynomials under a weighted version of the geometric volume element. And when we do so, we have a really nice hierarchy of spectral bases that live in the geometries of our choice and allow us to simulate rotationally constrained fluids. So the first example is the sphere. We have this square root of 1 minus s squared height function. So on the left here, we have Cartesian coordinates. It's our sphere with a spherical harmonic painted on its surface. And then on the right, we have our cylindrical coordinate, eta. And you can see this entire surface, the cylindrical bounding surface, maps to the equator of the sphere. So we did introduce a coordinate singularity, but because we have this h of s to the L factor in our basis functions, we explicitly handle that singularity. It doesn't become a problem for our numerical methods. And so then we can solve the linear onset to rotating convection problem. This is an eigenproblem that we set up in order to find the critical amount of thermal forcing that causes the fluid to turn over, to convect. And that critical forcing is dependent on the rotation rate related to the Ekman number. So you can see here, as rotation rate increases across and down, the structures become more and more vertically aligned. And so you can see here at the most rapid rotation that we solved, we have this really tall, thin cylindrical structures. And our spectral basis is really well suited to accommodating these. Another geometry we're interested in is the paraboloid. We can actually link these geometries up to experiments done at the UCLA Spin Lab, where they have a rotating bucket of fluid that's thermally forced, and they can actually measure the fluid flow inside of the container. And so that would correspond to this bottom figure here, where we have the upper half paraboloid. We set the bottom boundary to be z equals 0, and then we have this parabolic upper surface. And we can also do the full paraboloid, which has h of s on the top and minus h of s on the bottom. And here are a few of the damped inertial modes. And these are the modes that are restored by the Coriolis force. And you can see the decomposition in radial and vertical coordinates really well in these modes. So there's good high degree of radial oscillation, 0 vertical oscillations. Here's 1 vertical oscillation, and here's 2 vertical oscillations as we go left to right. So you can see this coordinate system, these stretched cylindrical coordinates are really natural for representing rotating fluids. Thanks.